Glad all of you aced your problems. What's expected of a Georgia Tech student. Just a few things for the future assignments I want all of you to keep in mind. It's good to have slides, as many of you did, but at the same time I would like you to use the whiteboard as much as possible, even if you're kind of repeating whatever is written on the slides, because I really want you to walk me through step by step. I mean, you did orally explain, most of you, in terms of what are the assumptions, etc. But it's nothing like actually writing on the board. So, because it's not like a lecture, it's more like a working out a problem. It's more like a tutorial, right? So it would be helpful if most of you used, or pretty much for all problems, I would like you to use the whiteboard, go step by step, but have this more like a prop. Not as the solution on the screen. What is real solution I want you to be having on the whiteboard. A few other things in terms of the consistency. I've been mentioning this before as well in terms of vectors and scalars. Sometimes I've been seeing some of the equations you've been left hand side is a vector and right hand side is a scalar. I can understand, of course, what you mean, because you're essentially talking about a particular measure number of that vector, but it's better to be a little more precise as engineers, especially when we communicate in a professional sense over here. It's good to have it more clearly in terms of the equations, the right hand side and left hand side matching in terms of the quantities. Okay, and some places I think who did it, you will know yourself. When you look at the primes and dots, it's important that you can I use this pens? Yeah. It's okay? Thanks. So these two quantities, one is the dot or the double dot, and also the if you're looking at the primes, the location of this is important. So the dots are always right on top in between. If you're looking at the font, it's kind of symmetric to that. Okay. So similarly with your double dot, whereas your primes are come after that. Okay, so in some places I saw the dots are coming over here, or the primes are coming over here. So just be a little. So this is not to be done. Okay, so these look like very minor things, but these are important from a perspective of being very precise, and that's how most of the formatting is done. Typically, people don't use Word and things like that for a lot of these publications. You use what is known as TeX or LaTeX, where you have far more precision in terms of the fonts and the special characters that you introduce, etc. Right? So let's get back to the class. We have some of the equations that we had in the previous class is what you actually used, and most of you have used all of these things. So let me just kind of summarize a few things that we got in terms of the simplicity of some of these things in how we have been doing these problems. So remember that we have introduced the Cartesian coordinate system. We have introduced the cylindrical coordinate system. Of course, special cases of that we have been looking at 3D and 2D as well. 2D as the special case of cylindrical would be polar. And something that we already introduced, but we will go a little more in detail today, is the intrinsic or natural. So these are the various coordinate systems. So just recollect that for every problem we are looking at introducing three aspects. One is the frame of reference. So for example, we could have a frame of reference I, let's say the inertial frame of reference, and for that alone is not sufficient. For that inertial frame of reference, we introduce a coordinate system. Okay, So in this case, we called it, let's say, to keep it as a special case as the planar, I'll put the x and y this way and put the z on this, right? So the first step is the frame of reference, and so far we've not been dealing with rigid bodies, we've been only dealing with particles. So the frame of reference could be a massless rigid body for all you know, okay? So it's an idealized kind of a situation. So that's your what you have as the frame of reference. The second aspect is to introduce these coordinates, and in many of your problems also I would like you to come up with this step-by-step approach. That way things become a little more clearer and when you go for more complex problems, okay? So that so the first thing is this, the second thing is the coordinates, and the third thing is the unit vectors which are tangential to these, right? So I hat, j hat, and k hat. Okay. Now also the origin associated with it, and it really doesn't matter for all practical purposes when you move the origin from this location to any other location, as long as you're not rotating this or transforming this. So it doesn't matter. Why it doesn't matter is that you're essentially looking at a particle which is moving on a certain path, that is your, let's say, your particle P, and then if you're looking at the position vector to it, it's essentially a straight line from O to P. Right? So this is your position vector P of the particle P from O. So this is one way of writing the position vector. You write as subscripts the particle which you are following and from where you are following. So what you are following is from is P, and we are following it from O. Another way of writing the same thing is to write it as O to P, okay, which you're familiar with, typically how you write in a lot of mathematics courses. But in many textbooks and literature in dynamics, you would see that it's the position of P with respect to O, okay. So now the reason why the translation of the reference frame doesn't make a difference is, suppose I have another reference frame. So let me call this as I star, for example, and the origin is O star for it, and you have the same things, the coordinates X star, Y star, and Z star, and the tangential unit vectors I star hat, J star hat, and K star hat. So you see that this is I star is the new frame of reference, which is different from I in the sense that it is translated. So there's a finite distance between O and O star, and there is a rotation as well, so that your X and your I and I star are not aligned with each other. Similarly, your J and J star and K star all hatted are not aligned with each other. They have an angle, non-zero angle between them. So they essentially it's a rotation. So even if one of them is non-zero, then essentially it's a different frame of reference that you're dealing with. On the other hand, if all these three axes had been parallel to the original set of axes, the translation should not have mattered. Okay. So it's only the rotations which will make a difference in terms of the measure numbers. Otherwise, the measure numbers will remain the same even if O is changed to O star. So if you're looking at the position vector, slightly changed with the Now this same point P that you're tracking on the same path that you have, just that now it is with respect to O star instead of O that you are tracking it with respect to earlier on. Now you can always write this vector P, which is going from O star to P, as a sum of two vectors, which is going from O star to O and then going to P from O, which is the original thing that we had over here. But this distance O to O star is not a function of time. These two are two fixed frames of reference, and therefore you see that this distance O to O star is not going to change. So in other words, this vector that you have here, P of O with respect to O star, is a constant. So now when you go to the velocity and the acceleration, when you're taking the time derivatives of this with respect to a particular reference frame, you will see that whether it is I or I star, this will be 0. This will be giving rise to 0. In other words, P dot and P double dot will be 0 for the first term, whereas the second term will therefore be equal to the first term in terms of the velocities and the accelerations, which is why it really doesn't matter where you actually put your O or O star. You put it the way it is most convenient for you to have the expressions in the simplest manner that you want. For example, if it were instead of a curved path, if it were, let's say, a straight line, then you would put it, you could put O or O star on the line itself, so that you deal only with, and also align one of your axes along that path. So it could be just a path that is something like this, right? So now I can put my origin at the beginning of that path, and I could align my X and I along that. Okay, it doesn't matter if it's not horizontal or vertical. So it's a question of, so in this case it's just rectilinear motion, and therefore we could take advantage of that and introduce, of course, Y and Z don't really matter in a problem like this, but just for the completeness you could introduce those two coordinates as well. But all of the action or the motion is happening on that line, which is now aligned with the X coordinate and the I hat unit vector. Now, so irrespective of which coordinate system you have, if you're looking at 3D, then essentially you have three components to it: the first, second, and the third. And in the Cartesian, for example, let's talk about the accelerations, or let's do all three of them. Let's talk about the position. Obviously, corresponding to one, you have I hat, and then you'd have X is the position that you have there, right? Similarly, you'd have Y over here and Z over here, and because I, J, K hats are all constants, they don't vary with time, your velocity would become just X dot along I hat, Y dot along J hat, and Z dot along K hat, right? And similarly, your acceleration would become X double dot, Y double dot, and Z double dot along those three corresponding unit vectors, I hat, J hat, and K hat. Okay, so that's what you have as the components. So this is the unit vector, this is the position, this is the velocity, and the acceleration. Okay, so now if we do a similar thing in the case of the cylindrical, you recollect what are the three unit vectors which you used for pretty much every problem today. What are the three unit vectors that you have there? What's the first one that you introduced? Yeah, so the unit vectors. So ER hat is the first one that we had, right? Then we had E theta hat, which is the tangential, and then finally because cylindrical, so it's the same thing as before, which is your k hat. Okay, so those are the unit vectors that you have. So coming to the position, how you define that. Okay, what was the position in the cylindrical coordinate? Anybody? Yeah. So r along er hat, right? What about what multiplies e theta hat? Theta. Are you sure? You're right. See, here you go x along I hat, y along j hat, z along k hat, right? So here you've gone already r along er hat. Okay, so remember that this is the er hat, and you've gone a distance r, which is the length of this vector p of o. You've gone a distance r along the er hat. Now you've already reached that point. You don't need to go any distance over the theta direction. So in other words, your e theta hat will have a 0 over here in all cases, general. Okay. Now for a 2D problem, that's done. You have only that. Okay. So in other words, there's only one term r e r hat. Okay. On the other hand, if it's a 3D problem, you would have the z coming in over here for a, or you could have, instead of cylindrical, you could have spherical, in which case you would have a 0 over here again, because there's nothing, just like there's no measure along the theta direction for the position, even the z, or the third coordinate, let's say, which is the phi coordinate, which is the this is azimuthal and this is polar, then you would have that also as 0. Okay, so you would have just r0 0 in the case of a spherical coordinate system. In the case of a cylindrical coordinate system, you have r0 z. Okay, so this is a very important thing. It's not just Daniel, but pretty much most students tend to make that mistake, that they say just by looking at this x, y, z, they think it's r theta z. Yes, it's the r theta z system, but when you're talking of the position vector, r alone takes care of both of these in the polar coordinate system. Similarly, in a spherical coordinate system, in fact, it takes care of all three. Okay, so just keep that in mind. Now coming to the velocities, which in fact we derived last time. So what is it along the ER hat? Remember? R dot, okay. Is that all for the velocity?
R dot E hat R plus R theta dot E hat.
Yeah, so you so that's in that term it's done. So what you're saying is will come over here, right? Because now you have that E theta dot, right?
Yes.
So E theta dot will term will come here. So what is that? What did you say? The source of that is, remember, this is r er hat. You're taking the time derivative of that with respect to the frame I. So you already have one term here because of the product rule, r dot er. Now you have to have something coming from r times er dot, and er dot is along E theta, right? So which is why you have a term coming here.
So the R dot E R dot term is in the first?
Yeah. Then here?
Then is that not the R theta dot?
Absolutely. Okay. So that's what you have over there. Next, what about this term over here? Yeah, same as before, right? Now coming to the acceleration is where you had two terms in each of them. This of course remains just as before, z double dot, almost trivial, whereas here you now end up with two terms each. So you look at this in terms of the Cartesian coordinate system. If you look at the same level of difficulty or complexity is there in all of them. They all have one term each. It's quite straightforward. Here you start with something very simple, because you have, instead of 3 that you had for the position here, you have only 2, and in spherical in fact becomes even simpler, just 1. But as you go for the velocity, it's somewhat of similar complexity level. In the case of spherical, you will have a term here as well, so it becomes a little more complex already in the velocity. But coming to the acceleration, you have far more complexity because of the time derivatives of the unit vectors associated as well. Here I hat, j hat and k hat were constants. Okay, so all 3 are constants. On the other hand, amongst these, here only one of them, which is k hat, is constant. The other 2 are varying with time. Okay, in general your er hat and e theta hat. Okay, they vary with s and therefore with time. Yeah.
I'm a bit confused as to why I hat, j hat, and k hat don't vary with time.
Yeah, so because we are considering all these derivatives with respect to so it's not, yeah. So all these velocities are with respect to that particular frame of reference, right? So in other words, I have to take the derivative of x times I hat plus y times j hat plus z times k hat with respect to I. Okay, and with respect to I have already defined I hat, j hat and k hat are fixed in I. Okay, so therefore they don't vary with time. Okay, whereas x, y and z vary with time, the positions of a particular particle. It could be one particle or many particles. Each of them varies with respect to time, but the unit vectors themselves don't. Clear?
Yeah. So how come then? What would the frame of reference be in the cylindrical case?
So in both these cases it is I. So once again we are taking, so it's the same quantity that we are dealing with. Okay, it's once again the velocity of the same particle p with respect to the same frame of reference I. But now the way the position is expressed is not in terms of I, j, k, but in terms of er, e theta and k, of which only one of them is constant. These 2 are varying, because as the particle moves, the tangential unit vector is this, right? And your radial, yeah, that's the and this is the radial or er hat, right? So I'm sorry. So I'm talking of the next one, the intrinsic. So here we have to talk of er hat, which I've already drawn, and e theta hat, which is perpendicular to that. Now you see, as you move from one point to another point, let's say take a point over here, the radial direction would be along the line joining O to, let's say, Q, right? So that in general will be different from this particular unit vector. So you see that as you change s, or you change t for that matter, because s is a function of t, you will see that the er hat and e theta hat are changing, which is why you will have a time derivative of both these, which are non-zero in general. Yeah. Anybody else? Any questions so far? Yeah. So now the acceleration has a term very similar to what we would expect an r dot, and here also you have an r theta double dot, but that's not all. Okay, so we have an additional term coming here and an additional term coming here. The additional term coming here is what we call as the centripetal, which is essentially your minus r, which is what you have here, right? R theta dot squared, right? And then here you have a additional term. So this is essentially your centripetal. And here you have your Coriolis, right? Which is twice r dot theta dot. Okay, so here you maintain the same level of simplicity or complexity throughout, going from position to velocity to acceleration. Here you start with a simple position, and then you go to similar level of complexity as you had for the Cartesian in the cylindrical velocity as well. But then when you get into acceleration, you have total of 5 terms to deal with instead of just 3 that you had over here. Okay, so just that things get complicated at different levels depending upon different coordinate systems that you use, but at the end of the day, it's what you want to intuitively get out of those derivations which makes your choice, and none of them is a right or wrong choice. It's up to you as a analyst to choose whichever is convenient for you, or whichever you're familiar with, or whichever is appropriate for the problem. So if you're familiar with all of them reasonably well, then you would choose the one which is most conducive for your derivation, makes this going from one step to another as simple as possible. So that way, and also you might get some interesting information which you might still have here, but it's kind of hidden within these two that you will get explicitly over here, right? So that's how it goes. So that's why these two are so very important over here. So today's class we will primarily kind of summarize that same thing for the intrinsic and natural system. But before we get to that, just a reminder of a few things, even though now that you have actually utilized these for pretty much every one of your homework problems, the 8 questions that you solved today, I would like you to see it from a newer perspective now that you have actually employed this, that both of them, the commonalities if you look at, both of them are functions only of the first derivative with respect to time, not the second derivative. So here you have only a first dot of theta, and here also you have only a first dot of r or a first dot of theta, right? Though in accelerations you typically expect a second derivative with respect to time, that's not to see. But nonetheless, you will have from the unit perspective or dimensionality perspective, it is appropriate because you have 2 of those theta dots. Okay, so there's a twice that you have the time coming in the denominator, and therefore you have a meter per second squared unit for both of these. The first one is dependent only on the existence of an angular velocity theta dot, whereas the second requires both an angular velocity and a radial velocity, okay, or radial speed, let us say, okay, because we have put everything in terms of scalar measure numbers here. So angular speed is just the presence of angular speed can contribute to this, no other speed is required, whereas here both angular speed and radial speed are required in order for Coriolis acceleration to appear. The other interesting thing is in this particular thing, the centripetal can go to 0 even when angular speed is non-zero at the center, because r of t is equal to 0 at the center, where if the path passes through the origin, for example, then at that location there will be no centripetal acceleration even though you have an angular speed, okay, because the rotation is happening around that. And then more than rotation, I would call it angular motion, because rotation is something associated with a rigid body. We are still talking of a particle. The particle rotation doesn't have any meaning, but the path is having a curved path, and therefore there is a center of curvature about which it is actually going around, right? So that is one thing to remember, and also the fact that the directions in which they are acting, one of them is radial, the other is in the tangential direction, and remember the sign. So this means minus ER. ER is always positive outward. So once again, you have to make sure that always in your problems ER is outward, not inward, and therefore with a negative sign it becomes inward. And the fact that there's a factor of 2 over here, because one came from the derivative of ER hat, the other came from the derivative of E theta hat, and both were similar terms, and therefore we just combined them with a factor 2. So these are the new terms that were not explicitly present over here. Doesn't mean that they are not there over here, just that they are contained within your x double dot and y double dot and don't appear clearly for you to see, whereas here they appear very clearly for you to see just because you have a new coordinate system. On the other hand, if you're just looking at the magnitude of the acceleration vector, if I take the magnitude of this particular vector, it would be exactly same as the magnitude of this vector for the same problem at the same instant of time, okay? And the direction, if I take all three of them, the resultant acceleration, it should be exactly same as what I get over here with respect to any same frame that we are comparing both the results with. Okay, so it's only a technique or a methodology or a process that is different. This problem is the same, the solution is going to be the same, just the matter of convenience and what you want to extract in terms of intermediate information will help you make the right choice, Cartesian or cylindrical. Not again a right choice, but an appropriate choice to get to some of the intermediate results. But from the final result point of view, pretty much every method or every coordinate system will lead you to the same thing. Okay, though I have not explicitly written, spherical goes along the same lines, just that things get even more complicated over here because of the presence of another angle over here instead of z, right? So let's now jump to intrinsic. So are there any questions on the Cartesian or cylindrical before we head on to this? Okay, now just to summarize the polar or cylindrical, we call it polar when it is 2D, and we call it cylindrical when it is 3D, right? So that's the nomenclature, just keep that in mind. But we can go to 3D not by introducing z k hat, but phi e phi, which will lead to a spherical coordinate system. We are not going into the details of that, but it's not. It's just a little more complicated than what we already did, but not something impossible to deal with. Okay. Now, again, the difference is much easier. Differentiation, rather, is much easier than integration. So these are similar kind of comments we made when we introduced the Cartesian coordinate system, and we said how to go from position to velocity to acceleration. It's through differentiation. So first derivative with respect to time, with respect to frame I. Second derivative with respect to time with respect to the same frame I. That's how we proceeded. If you're going in that direction, that is from the left side of the board to the right side, from the first column to the third column in this subset that you have, then you are essentially only taking derivatives, and it's quite easy. But many problems might, and you had a few examples of that as well, might be posed such that either the acceleration or velocity is given and you want the position. Okay, so you're going in the reverse order over here, and when you try to do that, things get a little messy, okay, especially in the cylindrical or spherical coordinate system, because you have non-linear terms. Because remember, it's not just the acceleration quantities like r double dot or theta double dot which are unknowns. The velocities are also unknowns, theta dot and r dot, and your position might also be unknown, which is r of t and theta of t. So when you're trying to go backwards over here, then the integration will involve nonlinear equations, and integrating them is not that easy, which is what I'm going to say in these many words on this particular slide. So the differentiation is much easier than integration, just like in Cartesian, here in polar and cylindrical as well. So wherein given the displacement that is given your r as well as z, then you have to get to the velocity and the acceleration. So it's very simple. I take the first derivative and the second derivative with respect to frame I, and I get to these. Okay. Only complication came in because of the fact that your ER hat was varying with respect to time. Therefore, it led to this particular term, right? So this is what contributed towards this, right? So it's because we had 0, so this would not have contributed anything. The source of this is because your ER hat was changing, and therefore this contribution actually came from here. Okay. Similarly, if you're looking at your r theta dot squared there with a negative sign and plus 2 r dot theta dot, both of these are contributing towards that, and eventually it's the coupling that is happening. So one thing is in terms of non-linearity, because r is an unknown, theta dot is an unknown, and then there is a square, there's a cubic level of non-linearity here. Here again, you have r dot and a theta dot, which is essentially a quadratic kind of a non-linearity that you have over here. Okay. So whereas here you see x, y, z, x dot, y dot, z dot, x double dot, y dot, double dot, z double dot are all unknowns. But in each of them, they are appearing linearly. So here it's a linear term, it's a linear term, it's a linear term. Okay, whereas here you see that non-linear terms have started appearing. The other thing is it's all x over here, it's all y over here, it's all z over here. But now here things are getting mixed up. You have r over here, but then the r is going over here as well, right? It's not only coming here, but it's coming here as well. Similarly, your theta is, though it should have come on this line, this row, it is coming not only here, which we would expect, but it's also coming over there. So in other words, it's not only non-linear, but also coupled. Okay, so that's the thing that you have to note over here. So analytical derivation is possible if you're going from the left to the right, given the position, if you're going to the velocity and the acceleration. But if you're looking at going in the reverse direction, either given acceleration and or velocity and going to the position, or from the acceleration going to the velocity, then things become a little more tougher, and because the equations involved are non-linear and coupled, involving both r and theta, you're not doing either one of them individually, but you have to solve for them simultaneously. Okay, so that's what this says. It's not straightforward because you have the acceleration, even though, just like, remember, we considered two cases in Cartesian coordinate system where the acceleration is given as a function only of time, okay, explicitly. And we also said that this can be given as a function of x and x dot as well. Okay, in other words, as a function of the position and the function of the speeds. Okay, so the second category was a little more complicated to solve compared to the first. In fact, most cases it required a numerical solver rather than an analytical solver. Same thing holds here. In fact, it becomes even more complicated to deal with, right? So even if the acceleration is only a function of time explicitly, the equations will be already nonlinear and coupled, as we already saw, because you're having products or squares, that is the nonlinearity, and the fact that both r and theta are present in the same term, that is how the coupling is happening. Okay, therefore analytical solutions of the integral are typically very difficult to there might be some special cases where you might be able to solve, but most cases you wouldn't. Okay, now given the acceleration, the calculation has to be done using numerical solvers, implementing them in a software. Either you write the code yourself or you use higher end languages like MATLAB, like some of you have demonstrated the use of that. Okay, now coming to the more realistic situation, in many cases acceleration is not only a function of time, but it's also a function of the state. The state variables are the position and the velocity. So the position in terms of r of t and theta of t, and in terms of their time derivatives r dot theta dot, and therefore it becomes even more complex. And if this itself required a numerical solution, it's quite obvious that this would require a numerical solution as well. But the fortunate thing is, even when you have this kind of a most complex situation that you can think of at this stage with particle kinematics, you would see that the only independent variable still remains time. Yes, we introduced an intermediate arc length s, but s is a function of time as well. So at the end of the day, you have only one independent variable, which is time, and that makes all of your governing equations ordinary differential equations rather than partial differential equations. On the other hand, when you go to more advanced courses to deal with more realistic structures, especially of aircraft dynamics, in the aircraft dynamics first course, you would still continue to deal with or treat the aircraft as a rigid body. That's fine. But eventually you have to bring in the flexibility of the material involved. In other words, the Hooke's law kicks in its more complex forms, a coupled form. Then you have all of these things are going to be dependent on not only the time, but also the location within the structure. So in other words, for example, if you take just a beam, at any location along the beam, if the coordinate is x, so that x coordinate also becomes an independent variable, just like time. So you have to follow each particle by its location and along time as what happens historically from the point t equal to 0 onwards that you are interested in. So then you would have not only nonlinear equations and coupled equations, but also partial differential equations that you have to deal with. Okay, and from the structural point of view, it will be a boundary value problem, and from the temporal point of view, it will be an initial value problem. So it will be a problem which is both having initial conditions as well as boundary conditions, and things become quite difficult to deal with. So I talked about a beam problem where only x is the spatial coordinate. In a plate problem like this tabletop that you are having over here, you will have an x and a y, and in most structures you might have to do a 3D model when you have x, y, z and t, which means 4 independent variables to deal with, and it will all be coupled, and becomes almost inevitable that you use a numerical solver. Any questions so far? Okay, let's go. So as I said, promised, we'll look at this now, the third category over here. Though the third category was spherical, which is kind of an extension of this that we already talked about. And intrinsic or natural is also something that I have been talking about in bits and pieces in my lectures earlier on, just that we want to make it a little more concrete now. So that's the 3D particle motion that we would like to deal with. Okay. So let me just clear the board for that. Okay. So there is a path of a particular particle that you are tracking, P. Okay. And as always, we introduce a frame I, and we have, let's say, okay, let's not introduce any coordinate system because we will try to deal with the coordinate system and the unit vectors associated with this, right? So now we have a position vector to that particle, which we are calling as P. So this is the origin O, so I can write it as P slash O, position of P with respect to O, right? Now you know that this is essentially like a one-dimensional motion. Even though it's a curved path, it's the S of t that is happening over here, and at some location we call that, let's say, S equal to 0, t equal to 0. Okay, or for some reason, if you're trying to follow the path before that, you might call it as S naught and t naught, so it doesn't make a huge difference in terms of the overall thing that we are going to be talking about over here. Now you introduce this particular system that you have, the unit vector system associated with P, which is going to be, first of all, the tangent, which we will call as Et hat. Then we introduce a normal, which we call as En hat. And then we have something that's perpendicular to that, which we called as the binormal, EB hat. Okay. So now how to get to ET hat is quite straightforward, because you're looking at on this path. Remember that the particle is not allowed to go perpendicular to the path. It also always has to go along the path, which means it is motion is tangential to the path. Okay. So if you're looking at the velocity vector v of this particular particle P with respect to I, so this is again a notation I would like you to utilize, either this or the velocity equivalently, the velocity of P with respect to I. Okay, the frame, whereas in the case of the position vector, remember both these are points. You're tracking a particular particle with respect to a particular point which is fixed on a frame of reference. Here you're talking about the velocity of a particle once again, but now with respect to not the specific point O of the frame I, but of the frame itself, which is I, because the time derivative is taken with respect to that. Okay, so this is the notation which is used. Some I might alternately keep jumping between these two, because this is used in a few books and this is used in a few other books. Both are acceptable. So either one essentially means that the time derivative of the position is taken with respect to I, okay, the frame of reference I. Now it's very clear that this particular velocity, because of the fact that this is a curvilinear motion, of which the rectilinear motion that we already studied is a special case, that it becomes a straight line. In other words, your curvature equal to 0. We already saw the Freinet-Serre formula, in which we put both tau and k to kappa to 0, and so it becomes a null matrix, and therefore you have all three of these unit vectors becoming constants, because their derivatives are equal to 0, right? So now, if that is the case, now if you can think of what is happening over here as the particle moves, you can think of, first of all, to introduce a particular concept so that your distinction between En and Eb becomes clear before we get on to the velocity. Now you see that there is a ds that is happening over here. In other words, a change in the s value. If you take 2 points, one on the which is infinitesimally to the left of the current location, the other to the right of the current location. In other words, one at t minus delta t, the other at t plus delta t. So now you have 3 points that you're dealing with. Okay. Now if those to just blow up what I'm talking about over there, so essentially you're talking of 3 points. One is your at t, the other is at t minus delta t, and the other is t plus delta t, and the arc length has of course changed, so it's s minus delta s over here and s plus delta s over here, right? Now the way I have drawn over here is appearing almost like a straight line over here, and that's how your tangent is essentially defined, your et hat, because eventually you're going to shrink these 2 points to that same location. Okay, but you could have a much larger curvature, in which case the curved path is like this. Your s is at some location, so your s minus delta s is over here, and your s plus delta s is over here. The difference between these two is that the 3 points that we are talking about, let's call them, let's say P, Q and R, are collinear. Okay, in other words, they are a straight line. So whereas here the same 3 points P, Q and R, if you join either P and R, any 2 points at a time, the third point will not be on that line. In other words, this is not collinear. So this is an example of when it's collinear, which is a simpler case. This is non-collinear. And if you deal with this, that can be treated as a special case. Now there's an important aspect of geometry that some of you might be familiar with, that if you have 3 points, then there is only one circle that you can draw which passes through all those 3 points. Okay, so that's not the path, but it's essentially a circle of a certain radius that you have over there, right? Now this particular circle is called as the osculating circle. Okay, so the etymology of this is that os is just means mouth and osculate is a kiss. So essentially your circle is kissing that particular path. Remember that the actual path of this might be something like this. It's not the circle itself, right? So that circle, you at each point you could have a different kind of a circle, unless of course it's a circular motion going around a circle, then the same oscillating circle is there at each and every point of the path. But here we are talking about an arbitrary shaped path that you have over here, and in an arbitrary shaped path like that you would have different oscillating circles at each point. And a circle is on a plane. Remember, just like 3 points will give you a unique circle, they will give you a unique triangle and a unique plane as well. And in fact that plane is called as the osculating plane. Okay. Now the reason why this is important is that this radius that you're talking about over here of that oscillating circle, 1 divided by that is what we already introduced as the concept of the curvature kappa. Remember, we in the Frenet's array formula we introduced this kappa of S. That kappa of S is 1 divided by a rho of S, which is essentially this radius that we are talking about, rho of S from a center. So I'm using O there, let me call this as O star. So essentially you're having that distance from the center of the oscillating circle to that particular point P, or Q or R for that matter, essentially is your distance rho, and the reciprocal of that is your curvature. So this is the curvature of the path. Now if you're dealing with this as a planar curve, then we are done with it. Okay, that's all that we need to know. But the same concept of oscillating circle and oscillating plane can be extended to the more generic motion, because now we are dealing with 3D particle motion. So the curve need not be a planar curve, it is essentially a spatial curve. Okay, so there's one level that we have moved from a rectilinear motion which is 1D to a planar curvilinear motion which is 2D, and then a spatial which is 3D. Okay, both of which are essentially curvilinear motion, just that when you are in rectilinear, both kappa and tau are 0. Okay, in other words, your curvature as well as your torsion are both equal to 0, not at a particular location but at all locations of the point of the path. Right, now coming to what is the complication from here to here? All that you did is you made your kappa not equal to 0. Let me say in this case you just made your kappa not equal to 0 in the 2D planar, but you continue to have your tau equal to 0. Okay, identically throughout the path. Okay, on the other hand, when you go to 3D spatial, here you bring in tau as well. So this is also not equal to 0. Okay, so that's how you're increasing the level of complexity, going from rectilinear to 2D planar curve to 3D spatial curve. And when you're doing that, all of these cases, this concept of oscillating circle still is valid. Okay, just that in the planar case, that oscillating circle and oscillating plane coincided with the plane of the motion. Whichever plane the motion is taking place, that plane itself is the oscillating plane, and you have many oscillating circles on that particular plane. Okay, that's the intermediate. What is the oscillating circle for your rectilinear?
I mean, would the circle be infinitely big?
Absolutely. So you have a same methodology, right? This is the point P. You're taking something which is infinitesimally close on the left, which you call as Q, infinitesimally close on the right, which you're calling as R. So essentially you're trying to shrink that. So now you have to draw a circle through that point. As you said, it's an infinite radius circle, okay, which means it's the same path. So in other words, it's a straight line. A straight line is the only one which has a 0 curvature, or it has infinite radius of curvature, going by the same thing that we wrote, which is 1 by rho, right? So 1 by rho So you're saying that rho is tending to infinity, which means kappa is tending to 0, which are equivalent of saying the same thing. So the path itself becomes the oscillating circle in the rectilinear motion. Okay, and of course the plane, again, there are infinite number of planes which can be suitable for that, including the plane of the whiteboard or perpendicular to the whiteboard or any angle with respect to that, as long as that line is passing through that plane, all of them are oscillating planes. Okay, so that is the case. Whereas in the 2D case, things are a little more clearer. There's a unique oscillating plane at each location, and which is the same at all locations, and therefore is only one. Once you come to the 3D case, the 3D spatial, you will have different oscillating circles, just like in this case, different radius, but also different oscillating planes itself, because at each location, those points P, Q, and R might not necessarily lie on the plane of this whiteboard. Some one or two of them might be away from that, and therefore essentially you have that. So when you have three collinear points, then you have a singularity that the circle becomes a straight line. But in all other cases, you would have the situation where you would have actual circles of finite radius. In this curved path itself, there can be a particular phase during which it is having a straight line. Okay, so in other words, a part of the path could be rectilinear also. Okay, so that's also included in us in our methodology. So which is why, even though we are going in small steps, baby steps from rectilinear to 2D curvilinear to 3D spatial curves, etc., all of what we learn is actually valid in the other situations, just it has to be generalized appropriately. So that generalization is what we are looking at. And in the general case, you could have parts in which those special cases might be appearing, like what we said over here. A part of this path could be a straight line, a part of this spatial curve could be a planar curve, etc., in which case as we move along, your kappa and tau are arbitrary functions of S. Some locations they might go to zeros, and if both of them go to zeros, then you have a rectilinear part of the motion, and when one of them goes to zero, namely tau, and kappa remains, then you will have curvilinear planar kind of a motion. Now, so that's as far as the oscillating circle is concerned. Now coming back to this distance that has been moved, which is the distance ds that we are talking about, that distance ds is what is going to contribute to your dp as well. So in other words, at this point P, I have a vector, and at some other location very close to it, I have the same point which has gone to R now, and so this vector is P going from O, so therefore P, position vector of P with respect to O, this is the position vector of R with respect to O, and I can write this as P plus dP. Okay, so if I call without loss of generality, if just call this as P, then this becomes nothing but P plus a dP, right? Whereas this is P, and this vector over here is dP. Okay, so now you see that I can go from this origin to P to I've already written P. Okay, origin to P, and then from P to R, or I can go directly from O to R. If I go directly from O to R, it is P plus dP. If I go via P, it becomes first P, that is what I go, and then a dP, right? So now all of these are with respect to your inertial frame of reference in terms of what is happening over a period dt, okay, that time dt that is taking. Now if you look at this distance, whatever is moved, obviously the magnitude of that, since all of the motion is happening on the curve, that magnitude of that particular vector dP has to be ds, right? Because the change is happening on that curve, okay, and it's happening in a tangential direction. Now if you look at, that is the magnitude of dP, whatever change in P is happening, it has to move from one point on the curve to another point on the curve, and changes on the curve are essentially measured by your arc length S, and therefore a small change, an infinitesimal change in that is ds, okay, over a period dt. That is essentially what is happening over there. Now you know that the direction in which it can go can never be perpendicular to that, because it has to be on the path, and therefore it is tangential to the path. And therefore now that we have the magnitude of dp and the direction of dp is parallel to et hat, and et hat by virtue of the hat on top is a unit vector, you can very easily see that dp itself will be its magnitude times its direction. Magnitude is ds and the direction is et hat, right? So that is your dp by dp, and this is your ds, right? Now if you look at and all of this we are looking at this change we are observing from the inertial frame of reference I that we have, because everything is linked to O in terms of the position vectors, that O is fixed in I, right? If that is the case, now I can bring the ds to this side, and I can see that your et hat is nothing but the derivative of p with respect to s, which we have been writing as p prime, okay? To be more precise, I should put an I, but if I define the primes as with respect to I, then I don't need to put the I over here, that p prime is with respect, always with respect to I, okay? So now if this is the case, remember that we have already talked about this, but I didn't give you the proof for that, okay? So we've been saying how is et hat a unit vector and things like that we've been discussing. Now you can very clearly see that that's the motion that it's, you can talk about it vectorially as dp or as the scalar measure number as ds, okay? Both are equivalent. Now that we know that the direction in which it happens is the tangential unit vector, whenever you take the derivative of the position vector with respect to the arc length in a curvilinear path, be it planar or spatial, doesn't matter. In both cases, the tangential unit vector is what will be the result of that derivative. Okay, so that's an important result that you have to remember, that p prime is equal to et hat. Okay, so that gets you the first of the unit vectors. Remember, I started off with a comparison of Cartesian with cylindrical. What did we write in each one of those rows? The first coordinate, the second coordinate, the third coordinate, x, y, z, and then we went on to the velocities and accelerations of that. Same thing here, the first coordinate that we're talking about is your tangential direction, et hat is the unit vector, and whatever is happening to in that tangential direction is essentially your coordinate. But things are not as clear in terms of the way we write the position vector. In the Cartesian, it was very clear. It was x times I hat plus y times j hat plus k times z hat. In the case of the cylindrical, it was just r times er hat. If it is polar, that's all. If it is cylindrical, then plus a z times a k hat. In the case of the intrinsic coordinate system, there is no general way to define your position. What it is more useful is in going for the velocity, because remember, we have already derived the expression for the velocity in going from this to this, because your dp by dt would be the velocity. Now what we have here is dp by ds, and I think in a previous class, Daniel, you pointed out that if you just multiply this by ds dot, you get dp by dt, and in fact for any quantity. So you have any quantity, if you have the primes, then if you let's say you want the dots, want the dot of a particular quantity, you already have the prime, let us say, all that you have to do is to multiply that by s dot. Why? Because this is nothing but a d by dt, this is nothing but a d by ds, and your s dot is nothing but ds by dt. So you see that this is the same thing on the left and the right hand side that you have, which is a d by dt. Of course, all of them are with respect to a particular, this doesn't matter because it's a scalar measure number, but these are for vectorial quantities. Whatever is the vector which is inside doesn't matter. So now the particular vector that we are talking about is the position vector p, and therefore its time derivative is nothing but the velocity. So that is the velocity of that particular particle p at that particular location, and that is given by multiplying this by s dot, which is why the velocity expression for p in the inertial frame I just becomes as simple as s dot along your et hat. Okay, this is the simplest expression for velocity that we have had. This is a three-dimensional expression, and we have only one unit vector on the right. In Cartesian we had I hat, j hat, k hat. In the case of the cylindrical we had two of them, er hat, and we had the in the position. But when we went to the velocity, even there we had er hat, e theta hat, and k hat. Okay, so in one of the simplicities in going to cylindrical we saw is a simpler expression for the position vector. But you see that we have now a simpler expression for the velocity itself. But the position becomes something which is dicey, because you can't so easily integrate this, because et hat, remember, is also a function of s. You have different tangential unit vectors at different locations. You start with this tangent vector and now you have come to this, and again the tangential vector keeps changing along the path s, and therefore as a function of time t as well, right? So therefore depending on what your focus is, or what quantities you are given and what quantities you want to determine, one of these methods becomes more convenient compared to the other. And if you want a simpler expressions for the position vector, the simplest case is spherical coordinate system. It's just r times er hat. Okay. If you want very simple expressions for the velocity, then the intrinsic coordinate system becomes very clear, because just one term that you have for the velocity, which is just s dot times et hat, right? Now if you want to get to the acceleration, obviously you will have this as well as this being functions of time, and you have to use the product rule in order to get to both of them, which means that you need an expression for et hat dot. Okay, just like in the radial coordinate or polar coordinate system, we dealt with taking the time derivatives of each one of these, or first of all with respect to the arc length and then with respect to the time. The same thing has to be done over here as well. So in this particular case, whereas the derivative of the position vector with respect to s is a unit vector already, when we go to the next level, we want to take the derivative of et hat. That becomes en hat, which is your normal vector, which is unit, but that derivative is not having a magnitude 1. So in other words, it's not a unit vector, you can't put a hat on it. So therefore you have to divide by its magnitude. So in other words, you want to get to your en hat, it is nothing but the time derivative in the inertial frame, or rather the s derivative of your et hat. Okay, but that's not a unit vector, and therefore you will have to divide by its magnitude. Or you can put all of these as primes, doesn't matter. Now this will give you always a unit vector which is in the osculating plane. Of course, in the 2D case it becomes a trivial thing, but in a 3D case it becomes very important result that you can actually benefit by, that this normal is in the oscillating plane. Tangential is already in the oscillating plane. Now the normal is also in the oscillating plane. So et and en together define that plane for you. Okay, and anything which is perpendicular to the oscillating plane is what we are calling as EB, because now EB is going to be defined as the cross product, as we already did. This is also a definition. Okay, so this EB hat is defined as your ET hat crossed with your EN hat. Okay, any questions or doubts on this so far? We'll try to summarize that in the slides as well. Okay, so when you have, just raise the question, I'll come back to that. So let's just go back to this. Okay, so what did I say? Yeah, so it's a general 3D motion that we are looking at, which means a spatial curve, of which the planar curve will become a special case, and two names given to this set of unit vectors, ET, EN and EB. Either you can call them as natural coordinate system or intrinsic coordinate system and the corresponding unit vectors. Okay, now coming to the path that you have, pretty much most of these things I've already explained on the board, so I'll just go through it. So this is the path that you have. It could be a spatial curve. It could be, though I've drawn it on the screen over here, it essentially could come in and out of the screen as well, right? Now you've introduced the inertial frame of reference, the coordinate system associated with it, unit vectors associated with it, but none of them you're going to actually utilize because we're going to use something which is natural or intrinsic to the path itself, which is why we locate a particular location, arbitrary location on the path, which we will define by this position vector P of t. And once we have that for this particle, or the same thing, even though we are doing only particle kinematics right now, a lot of this will be taken forward for your rigid body motion, because rigid body motion can be considered to be two parts. One is essentially your translational motion, and the other is your attitude changing, which is your rotational motion, right? For the translational motion, we are going to follow essentially a particular point of the rigid body. It could be a part of the material. It could be, for example, if it's a hollow sphere, it could be where there is no material, or it could even be outside that, but it's essentially connected to that rigid body and moves along with the rigid body. That's the point that we are interested in. And more often than not, it would be the center of mass, which I will abbreviate as CM. That center of mass is what you will typically be dealing with. So pretty much everything that we are talking about now for a particle will be valid for that center of mass. It's just that we have to jazz it up with the rotational motion as well, and there lo and behold you would have the 3D motion of the rigid body built up over that particle, because you can think of the rigid body as a combination of a set of particles. Okay, so those particles are making it up, just that the distance between them remains the same, which is how you define the rigidity of that particular body, and that we will bring through a constraint later on when we go to it. So right now we are still with the particle kinematics, and we're looking at that. The path of the particle is given by P of t. So the position vector in terms of the coordinate along the path, which we had defined as S of t, remember. So that in terms of that, it's just some arbitrary function P of S of t, right? Because that depends on many things. One is the path itself. The other is your choice of the initial frame and where you have put that origin O in particular, okay? Because this vector P depends on 2 points. One is a point on the path and a point from which you are measuring the position vector. So the choice of this origin will make a difference in terms of what this position vector is, right? But what we are interested in is not just the position, but essentially the how the change happens, which means the motion happens, which means the velocities and the accelerations that are involved. So S of t is the arc length coordinate, which is a function of time, and the distance traveled along that path is what that actually measures. So essentially, on that curve, you're measuring the total distance that is taking place. It's not the magnitude of the displacement joining these 2 points, okay? So that would be the shortest distance going from here to here, but no, you're actually accumulating that. Typical to what you study in integral calculus is a line integral, right? So you go along the path and you integrate to get the essentially like the perimeter of that whatever you're covering the distance, right? So that's your S of t, and how this is a function of p, how it's a function of s is not of much consequence for us at this point in time, okay? Because we can see that without knowing your p, how it is a function of s, you can get to the velocity already with the simplest expression that is there, which is your s dot et hat, okay? Since you have this advantage, this is something that you typically don't visit in terms of the actual functionality of how p is a function of s. You really don't care for most problems. Now coming to many of the things that I already explained on the whiteboard. First, the tangential unit vector. So that's along the path, and as we saw, it's just a p prime, okay? I have not put the explicitly the frame with respect to which it is taken. That's important. So this is with respect to I, because that's the only frame that we have introduced. That's the default frame, and therefore you see that that is left out over there. But I would urge you, when you do your homeworks, not to do the same thing. So coming to Vp, so now it's not a derivative of P with respect to S, but it's a derivative with respect to time. Okay, so that's the only difference. But then we have the simple chain rule that we have. So you take the derivative with respect to S first, and then the derivative of S with respect to T, which is nothing but simplified as S dot, and therefore you have S dot times your Et hat. Okay, now the velocity is always by definition in tangential direction. Okay, that's how you define the path. The path of a particle essentially means that the velocity is always along the tangent, otherwise you wouldn't even call that a path. Okay, so now for example, that could be in the case of the aircraft motion in the atmosphere, it would essentially be the so-called wind axis, which is how you define the velocity vector V infinity. And that velocity vector, with respect to that, you're essentially measuring certain angles of certain lines which you are defining on the aircraft. For example, there's a line called the zero lift line of the aircraft, and so if the zero lift line is aligned with the velocity vector, essentially your angle of attack is 0, and therefore you don't have any lift, and which is by definition of the zero lift line. And therefore you would use that body fixed geometry of the zero lift line along with the motion which is prescribed by your V infinity vector in order to define those angles. And this is of course for the symmetric motion in the plane of symmetry of the aircraft, where only altitude is changing or your forward motion is there, and also the pitching motion is there. But once you bring in the other three motions, namely your roll, yaw and or side slip, things become a little more dicey, because those three are involving two rotations. And as of now, we will just talk only about the side slip beta, which is essentially again that velocity vector, what is the angle it is making with that plane of symmetry of the aircraft. Okay. On the other hand, your angle of attack is the angle between the zero lift line ZLL and the velocity vector. So both cases, the definition is with respect to your velocity vector, the relative velocity vector between the air and the aircraft, which is your V infinity vector, and that is making a certain angle with the zero lift line, which we call as alpha, and it makes a certain angle with the plane of symmetry of the aircraft, because the starboard and the port are similar. So essentially the plane of symmetry, in fact your zero lift line is also passing through that plane of symmetry, and that angle between the plane of symmetry and your V infinity vector is what is called as beta. Okay, so these two to a large extent determine the aerodynamics of the motion, and then many things are dependent on that, and eventually you try to go to all of those things which are part of your aerodynamics or aircraft dynamics and things like that. We will not venture into that. I'm just giving this example only in passing. Okay, so for example, this whatever we are talking about, this unit vector Et hat that we have defined here as the tangent unit vector to the path is not necessarily a constant in the body fixed frame. Okay, so the body fixed frame of reference could be A, just like this is I, this is the aircraft which is flying, and that aircraft, let's say you're talking about the center of mass of that particular aircraft is what you're following in this path. In other words, it could be a fairly complex maneuver that aircraft is performing, and that path that you're talking about is the path of the center of mass of that particular aircraft, right? Now you're following that. So that therefore your Et hat is tangential to that path. It need not be a constant in the aircraft. In fact, most cases it won't be, because that tangential path, because the orientation of the aircraft at different times might be different with respect to this particular path in order to be able to achieve something like this. In fact, I think you probably didn't have, did you have one question related to that? I think probably in the next homework you would have some question relating to the pull up or pull down maneuvers, right? Okay, yeah. So that's, so you will see that it's in general, it's not something which is fixed in your body frame of reference. but it's essentially path dependent quantity, and in order to be able to have such a complex path, your body's orientation will keep changing, whether it's the pitch, just the pitch in some cases, simpler maneuvers, or the roll and the yaw as well in other cases, and in which case it's not a single line along the aircraft which is that tangential unit vector. The tangential unit vector is a property of the path, not of the aircraft. That's something that you should be aware of. Whereas in the case of, let's say in many situations when you're using the Cartesian coordinate system, you could define your x, y and z with respect to the aircraft. One, let's say from the center of mass passing through the tip of the nose, you could call it as x-axis. Then you could call the one passing through one of the wings as your y-axis, and again from the center of mass. Again, the third one from the center of mass, which is perpendicular to both of these, you would call as the z-axis. Not necessary that your x-axis is horizontal or z-axis is vertical all the time, depends on the orientation of the aircraft, right? So that's the body fixed frame of reference. Whereas I am repeatedly saying, because a lot of students who are exposed to this method tend to confuse your ET, EN and EB system with the body fixed frame of reference. They need not be the same, and in fact they will change with respect to time as well over a even simple maneuvers. So example, it may not be along the aircraft nose from the center of mass, though typically for most situations it's close, because these angles, remember, alpha and beta, because alpha beyond a certain point leads you to the stall, and therefore you can't go beyond a certain value. Similarly, side slip is more encountered in regular passenger aircraft when there is a sideward gust or a component of the wind is having a sideward velocity, and therefore you would have something like that, which is typically not as large compared to the velocity of the aircraft itself, and therefore the side slip angles, which is derived as a ratio of those, will typically be fairly small as well. So typically small, and they will measure the body's orientation with respect, I'll stop with this slide, body's orientation with respect to the tangential velocity of the unit vector, which is nothing but your V infinity vector that I was talking about. So as I said, the advantage of this method is a simple expression for velocity, but the disadvantage is that you cannot write the position vector for the general case, like we were writing x, I, y, j, k, z, k, etc., or just r, e, r plus z, e, k. These kinds of things we cannot write in this case, but that's the price we have to pay for the simplicity in the velocity, and therefore even the acceleration would be the simplest that you have seen so far, which we will see in the afternoon session. Okay, so we will resume at 2:15.